Algebra 1 students, welcome to today's 6.3 notes. Make sure you're following along and working with this. I think you'll find these to be helpful to you. All right, we'll look at a few examples, but first let's talk about the new strategy we're using. We've talked about two ways previously to solve systems. First, we looked at graphing. Next, we looked at substitution. Today we're going to look at a third option we call elimination. I'm going to read some of this up top, but it says the addition property of equality tells us that if A equals B and C equals D, then A plus C equals B plus D. In other words, you can add those two equations together, add the left sides together, add the right sides together. It works. Extending that logic, we can use that to add algebraic equations like you see, or linear equations as we use. And if we do that strategically, we can eliminate variables and solve for other variables. We call the process elimination. I think you'll like this method. It's one that I personally really like and use quite often. All right, so let's take a look at the first one. 3x minus y equals 11 and 5x plus y equals 5. Here's what I notice right away. Negative 1y, positive 1y. We're going to add these together. 8x, you notice negative y plus y is just 0y, so I can just leave that out, equals 16. This worked out pretty nicely, didn't it? We can divide both sides by 2. Excuse me. Let's try that again. We can divide both sides by 8. That's what I get for thinking ahead, and we know that x equals 2. Next, you can plug in that value. You can choose whichever equation you would like. I'm going with the first. There's nothing about the first equation that's better than the second. It's just the one I'm using. And I get y equal to negative 5. So my solution then is an ordered pair would be the point 2, negative 5. You could get that same answer by graphing. You would find that that's where the two lines intersect. If you use substitution, you should get the same answer as well. Of course, it always is possible to go ahead and check your solution to negative 5. I would plug it into the second equation since we used the first to solve for y. 5 times 2 is 10 plus negative 5, so 10 minus 5 is 5. That's absolutely correct. We've got a good answer. On our next equation, we'll have to do a little extra work before we can eliminate a variable. Now what I notice is I have a negative 2y here and a positive 4y in the second equation. So I'm going to multiply the first equation by 2. 2x plus 2x is 4x. The 4y's are eliminated. 4 plus 16 is 20. So we know that x is then equal to 5. Then you could choose first equation or second. I'm going to go with the second one this time. Again, like I previously mentioned, it really doesn't matter which equation you use. That's 10 plus 4y equals 4. So we'll subtract 10. And finally divide by 4. Now negative 6/4, I'd want to go ahead and simplify that to negative 3/2. So our solution is the point 5 and negative 3/2. Again, if you wanted to check your answer, you could plug these values in to the first equation. 2 times negative 3/2. I know you guys don't like messing with the fractions, but 2 times 3/2 is okay. That's just simply negative 3, but you're subtracting it. So what you have is 5 plus 3 equals 8, and that is true. All right. Now there's another scenario we haven't had to deal with yet, and that is at times you have to multiply both equations by a factor in order to eliminate a variable. And this is one of those. Now I'm going to work on eliminating x's primarily because the coefficients in front of x are both small numbers, a 2 and a 3. It wouldn't be that big of a difference to go for the y's, but I'm going to go for x's. So what I'm going to do is multiply the first equation, everything by 2, and the second equation by 3, but I want to make it negative so that I can have some terms cancel or eliminate. So let's rewrite these. 6x plus 4y equals, and don't forget 17 times 2 as well, so equals 34. Then we'll have negative 6x minus 15y, and 76 times 3 is 78. We have to make sure it's negative, and there we go. Now the nice thing about this, as we've seen before, one of the terms is now eliminated. 4y plus negative 15y, and then 34 plus negative 78 gives us negative 44, and that's the kind of numbers we like to see. Evenly divisible, integer solutions. Life is good. Let's go ahead and plug that value, the y value, so 3x plus 2 times 4 equals 17. And then we'll just simply go about solving for x. So our ordered pair is the point 3 and 4. I might sound a bit like a broken record, but you could find that same solution by graphing. You could find it by substitution. What you won't always find is the shape of Kansas outlining my answer. I don't know how that happened, but there it is. All right, let's take a look at the next one. And yes, I'm a loser. You don't have to tell me that. I already know. What I'm going to do on the first equation is I want to multiply everything by 2. I'm going to do that so that I can get rid of x values, but we have a strange occurrence here. X values are gone and y values are gone. We've eliminated 2 things. I think you guys know this, but 0 is not equal to 60. So what we say there is no solution. Why would there be no solution? Well, these are lines that are parallel. Okay, let's take a look at number 5. Cruising right along here. It looks to me like we're going to have to do 2 steps of multiplication here. So I'm going to multiply the first equation by 3 and the second by negative 2. By doing this, I'll be able to get rid of my x values. So 6x minus 12y is equal to negative 24, and negative 6x plus 12y equals 24. Interesting. 0, 0 equals 0. How does that happen? Well, these 2 lines are actually one line, and we call that infinite solutions. 2 lines that are exactly the same. All right, last one, a little application problem for you. 2 families decide to attend the Olathe South musical. And one family, 4 adults and 3 children, attend. It costs them $47. Another family has 2 adults and 4 children. It costs them $36. Find the cost for an adult ticket and the cost for a child ticket. Now, this last sentence, to me, is really key. It tells us what our variables would be. Usually we use x's and y's. Since we're not graphing, I'm going to go ahead and just use A and C, where A represents the cost of an adult ticket and C represents the cost of a child ticket. Let's look at this one family at a time. The first family has 4 adults. I can represent that with 4 times A. And 3 children. 3 times C. And it costs them $47. By the same token, the second family, 2 adults, 4 children, $36. All right, let's start working on simplifying this. And I think what I see is the simplest option here is to take this second equation by -2. It's probably worth pointing out that this is not the only option, it's just one option. But I'm going to rewrite the first equation, and then I'll have -4a minus 8c equals, and 36 times 2 is 72, and it of course has to be negative. We've eliminated the a values, so we're going to have -5c equals -25. 72 and 47 have a difference of 25. The negative number is the larger of the two, so that has to be negative. And I know then that c is 5. Okay, I've got one more thing I need to do here, and that is to find the cost of an adult ticket. I can use either equation. I'm going to go with the first. So I know 4a plus 3 times 5 has to equal 47. So 4a plus 15 equals 47. If you subtract, you'll get 32. And then divide, and you get 8. We need to make sure we put this into terms that make sense in the context of the problem. It says find the cost of an adult ticket and find the cost for a child ticket. So I would say something like one adult ticket costs $8 and one child ticket costs $5. All right, folks, that is the end of the notes. Have a great day. Come to class ready to work hard.